All right, so in today's class, we are going to be talking about the density of an atom. So you can write, density is defined as mass of an atom per unit volume of the atom. The density of an atom is defined as the mass of the atom per unit volume of the atom. It is defined as the mass of the atom per unit volume of the atom. So mathematically, we can say density of an atom. So call this D is actually mass of the atom, okay, all over volume of the atom, okay, volume of atom. So we can say this mathematically for an atom that density is mass all over volume. But what is this mass and what is this volume? Okay, what is this mass of an atom and what is also this volume of the atom? Recall from your elementary chemistry, you know that the amount of a substance, which is symbolized as N, small letter N, is given as the mass of the substance, okay, mass of that given substance all over molar mass. You already know this, molar mass of the substance. So this is equal to mass for capital M all over, okay, mass for small m all over molar mass for capital M. So this simply means that amount N is equal to mass all over, the capital M stands for molar mass and the small m stands for mass. And that means to find the mass of every atom, we can simply cross multiply the amount multiplied by the molar mass. This simply implies that the mass of this atom or mass of any atom M is equal to what? Amount times the molar mass of the atom. So this means that the mass of an atom is simply amount times molar mass, where N gives us the number of atoms. Okay, N simply means the amount of atom involved. Okay, yeah, where N equals amount or number of atoms. Okay, where N equals amount or number of atoms, and M there, the capital M there stands for what? The molar mass. You're following, right? Okay, capital M stands for the molar mass. Then, what is the volume of the atom? Okay, from Avogadro's hypothesis, the volume of every atom from Avogadro's hypothesis, okay, Avogadro's hypothesis, from Avogadro's hypothesis, we have that the volume of an atom, okay, volume V is equal to the volume of the atom multiplied by the Avogadro's number. So call this AV. Okay, the volume of the atom multiplied by Avogadro's number. And Avogadro's number is given as 6.02 by 10 to the power of 23. So this actually becomes V times 6.03 by 10 to the power of 23. So always remember to multiply the given volume by the Avogadro's number. Okay, that gives you the entire volume of the atom. So if we represent this now, if we represent this into the equation for density, we can obtain that the density of an atom D is equal to, we said, mass of atom, and we obtain the mass of atom to be what? Amount times molar mass. So you simply have N times molar mass all over all over. Then we obtain the volume of the atom itself to be volume of atom multiplied by Avogadro's number. This becomes V times, okay, Avogadro's number, V times Avogadro's number. So we have this. We have V stands for volume of atom. A is the amount, which tells us the number of atoms present in the given structure, and M is the molar mass. Of course, V is the volume, and AV becomes the Avogadro's number. All right. So let's pick up. Before we pick up a problem, let's first of all understand something. Okay, that we're going to be needing very, very quickly. Okay, as regards to this video. The first thing we'll understand is that for simple cubic structure, I've said it before, the relationship between a lattice parameter and the radius is given as A is equal to 2R. That's for simple cubic structure. Whereas for the body center cubic structure, BCC, the relationship between the lattice parameter, which is A, to the radius is simply 4r all over root 3. You have this. And finally, for the face-centered cubic structure, FCC, the relationship is equal to A equals 2r root 2. Keeping this in mind, another thing I want to call to your attention is the number of atoms present for a simple cubic structure, okay, considering the number of atoms here, n, okay, considering the number of atoms, okay, n, for SC, for simple cubic, n is equal to 1. For, okay, for body center cubic, BCC, the number of atoms is equal to 2. Okay, for body center cubic, the number of atoms is equal to 2. And for face center cubic, FCC, the number of atoms is equal to 4. So we've done all this on our video. So I did a video on crystallographic planes. Okay, so I'll post the link of that video in the description of this particular video, so you can watch that all up to grab, okay, how we got these values. Okay, but for just have it in mind that for the simple cubic structure, n is equal to 1. For the body center cubic structure, n is equal to 2. And for the face center cubic structure, n is equal to 4. Having this in mind, let us pick a problem to now explain the density of an atom. Now take down this question. Okay, take down this question. Sodium fluoride crystallizes into a face center cubic structure with lattice parameter of 4.05 Armstrong units. Calculate the density of sodium fluoride. Okay, so let's get down the question now. We are given the atom to be a sodium fluoride, and the condition says that this atom was crystallized into an FCC, okay, FCC structure. It was crystallized into an FCC structure. All right, so considering the formula for density, we need to calculate the number of atoms and the molar mass, and of course the volume. Now, the number of atoms for FCC structure, N is equal to, we've said here that for FCC structure, N is equal to 4. So for FCC structure, N is equal to 4. Then again, we need to compute the molar mass of sodium fluoride. And the molar mass of sodium fluoride involves the sum of their entire masses. The molar mass of sodium itself is 23. So you have 23 plus molar mass of fluorine. Fluorine is 19. And if you add these two all up, you're going to have 43 or 42 gram per mole. So the molar mass of sodium fluoride is actually 42 gram per mole. Having known this now, we are also given the lattice parameter. Lattice parameter A was given to us as 4.05 Armstrong units. Okay, so we have to convert this to centimeter. To convert this value to centimeter, simply multiply it to what? Multiply 4.05 by 10 to the power of minus 8. It becomes in centimeter. Okay, so this becomes 4.05 by 10 to the power of minus 8 in centimeter. All right, so that becomes the value of the lattice parameter in centimeter. But then we need to compute the volume of this cubic structure, or the volume of this atom. All right, so the volume is, since it's a cube, the volume of the cubic structure, volume V, is equal to A to the power of 3. We've said this previously in our videos. So this becomes, now we know the value of A now. A is 4.05 by 10 to the power of minus 8, all to the power of 3. So this simply implies that the volume of this cube is equal to, please give me 4.05 by 10 to the power of minus 8 to the power of 3. All right, so we have 6.64 by 10 to the power of minus 23 in meters cube. This becomes the volume occupied by this sodium fluoride. So if we know this now, we can now compute the density of this atom. Simply, density is equal to, N stands for the amount of atom, and for FCC, N is equal to 4. So this becomes 4 multiplied by molar mass of sodium fluoride. We had that to be 42. So that's 4 times 42 all over we have the volume of sodium fluoride becomes 6.64 by 10 to the power of minus 23 multiplied by the Avogadro's number, not forgetting, which is 6.03 by 10 to the power of 23. Okay, so please give me this multiple. This is equal to 4 times 42 gives us 168 all over 6.64 by 10 to the power of minus 23 multiply 6.03 by 10 to the power of minus 20, sorry, by 10 to the power of 23. So we have 40.03. This now implies that the density of sodium fluoride becomes what? 168 divided 40.03. So we have 4.2 gram per centimeter cube. This becomes the density of sodium fluoride. Okay, so it's not just to calculate density. We can also be given a question and we are asked to determine which type of cubic structure a particular atom belongs to. Okay, so not just to compute the density, we could also be given a question to determine what type of cubic structure a particular atom belongs to. So I'll pick up a question like that for us now. Okay. All right, so let's consider this question. Take down this question, please. An atom having a lattice parameter of 2.882 Armstrong units has an atomic weight of 52 grams. What type of cubic structure is this atom if its density is 7.29 gram per centimeter cube? Are you there? Okay. So in this case now, we weren't given the cubic structure, whether it's an FCC or whether it's a BCC or an SC. So all we need to do is, from the formula of density, notice that in that question we were given density. Please call me the parameters. We were given density, right? Okay. Density D is equal to 7.29 gram per centimeter cube, right? All right. What else was given? We were given lattice parameter. A was given as what? We have A was given as 2.882 Armstrong units. So we can convert this to meters or centimeter since the density is in gram per centimeter cube. So convert this to centimeter, it becomes 2.882 multiplied by 10 to the power of minus 8 in centimeter. We were also given what there? Molecular weight. Okay, the weight of the substance was given M. Molecular weight was given as what? Was given as 52 gram per, okay, per mole. So the molecular weight of this substance was given. So we know the molecular weight, we know the density, we are given the lattice parameter, which means we can compute the volume, and we know Avogadro's number. All we need to do is to what? Make N, which is the amount subject of the formula, and investigate the value of N to know what type of structure or what type of cubic structure that particular atom belongs to. All right, so from here, if you make N subject of the formula here, okay, if we make N here subject, it means that N is equal to, this will give us D times volume times Avogadro's number, okay, all over molar mass. Okay, so this becomes the value of N. If we make N subject of the formula from here, simply cross multiply, D multiplies the whole of this, okay, then to make N remain alone, divide through by what? Molar mass. You have that. All right, so let's compute the volume. We know the lattice parameter, therefore we can find volume to be equal to, remember, volume is simply 8 to the power of 3. So this is equal to 2.882 by 10 to the power of minus 8 all to the power of 3. All right, so give me the value of this volume. V is now equal to, so we have 2.4 by 10 to the power of minus 23 centimeter cube. This becomes the value of the volume. Having known this now, we can now compute value for the amount. N is equal to, so we said density. Density was given as 7.29. So you have 7.29 multiplied by the volume, we have the volume now, 2.4 multiplied by 10 to the power of minus 23 multiplied by Avogadro's number, and Avogadro's number remains 6.03 by 10 to the power of 23 all over the molar mass of the given atom, and its molar mass was given as 52. So all over 52. So n is equal to, give me everything at the numerator, 7.29 by 2.4 by 10 to the power of minus 23 by 6.03 by 10 to the power of 23. So we have 105.50 all over 52. So 105.50 divided by 52. This gives us n to be equal to 2.0. So n is equal to 2. And since n is equal to 2, recall we said earlier that when n is equal to 2, it means that this structure is actually what? A BCC structure. Hence, the atom, okay, the atom has a BCC structure. All right, so the atom has a body-centered cubic structure. So you can also use this formula to identify what type of cubic structure which belongs to any given atom, not just to find the density of the atom. So final question, finally, please take down this question. Aluminium has a face-centered cubic structure and an atomic radius of 1.28 Armstrong units. What is the density of aluminium? So quickly, let's get down the parameters that was given to us. We were given first that atomic radius was given, okay, atomic radius was given R to be equal to 1.28 Armstrong of units. So convert this to centimeter. This becomes 1.28 by 10 to the power of minus 8 centimeter. All right. So simply multiply that to 10 to the power of minus 8. That becomes the radius of aluminium. We were also given the okay, we have the radius. Now the atom itself is an aluminium, Al. So we need to find the molar mass of aluminium, please. What is the molar mass of aluminium? The atom itself given to us was Al, that's aluminium. We need to find the molar mass of aluminium. 26. Yeah. So the molar mass of aluminium is actually 26 gram per mole. So this gives us the molar mass of aluminium, 26 gram per mole. So we are asked to compute the density. Now, it was stated that aluminium has FCC structure, okay, FCC structure. Therefore, the number of atoms, remember, for FCC structure, number of atoms is equal to 4. So which means N is equal to 4. So we know the number of atoms, we know the molecules involved, we know the, of course, Avogadro's number is known. All we need to do is to what? Compute the volume. But to find the volume, since for FCC structure, I've said that since aluminum has FCC structure, remember the lattice parameter, the relationship which the lattice parameter has with radius for FCC structure is given as what? A equals 2 r root 2. So don't mistake this. Don't go and say because you have a radius, you can calculate the volume with the radius. No. Okay. All you need to do is simply what? Find the lattice parameter first, because we are only given radius. We need to now compute the lattice parameter. Therefore, lattice parameter A is equal to, for FCC, is equal to 2 r root 2. This is now equal to 2 times the radius. Radius is given there as 1.28 by 10 to the power of minus 8 multiplied by the square root of 2 is 1.14, so 1.14. So give me these multiples together. Therefore, the lattice parameter A is equal to, give me those multiples together. So you have 2.92 by 10 to the power of minus 8 in centimeter. This becomes the lattice parameter. Hence, we can now find the volume. Okay, therefore, volume, remember, V is equal to A to the power of 3, which is now equal to 2.98 by 10 to the power of minus 8 all to the power of 3. Please give me this volume. This implies V is equal to, so you have 2.65 by 10 to the power of minus 23 centimeter cube. This becomes the value of the volume. So if you know this, you can now compute the density of aluminium. Density D is now equal to N. The number of atoms for FCC is 4. So you have 4 times the molar mass of aluminium. Will obtain that to be 26. It become 4 times 26 all over the volume of aluminium. We've obtained that here, 2.65 by 10 to the power of minus 23 multiplied by Avogadro's number, 6.03 by 10 to the power of 23. So if you do this all together, give me the numerator, 4 times 26, you have 104 all over, give me the denominator, 2.65 by 10 to the power of minus 23 multiply 6.03 by 10 to the power of 23. So you have 15.98. All right, so we now compute 104 divides 15.98. This implies that the density of aluminum is 6.51 gram per centimeter cube. Okay, so that's how you find your answer. Now, in this case, if a radius is involved, then you have to consider the particular cubic structure and then relate if lattice parameter to what the radius from these formulas given to you on the board. Okay, from the formulas given to you on the board. That's how you solve when a radius is involved. All right, guys. So I hope you find this video interesting and helpful. Please, if you do, I would like you to leave your thoughts in the comment section. And of course, if you're new to the channel, do well to like, share, and subscribe on this channel as well. I will see you in the next video. Thanks and cheers.